Yeah, you're gonna miss the first part, I guess. All right. So let's let f of z and g of z be complex valued functions, okay, defined for z lives in some domain D, which is a subset of the complex numbers, okay, then we can say that f of z is equal to big O of g of z, z for z being in D, if there exists a constant k greater than 0 such that the absolute value or magnitude of f of z is less than or equal to k magnitude of g of z, okay, for all z that live in D. This is gummed up. Okay. And we would say that f is big O of g in this case, big O notation. Okay. So we're usually interested in behavior near some limit point, okay? So typically we draw this domain D in some tight neighborhood around the limit point for us to sort of care about the scaling, right? If Z is, if we're talking about epsilon stringing to 0, we don't much care about how the scaling looks, maybe as epsilon is order 1, but much smaller than that, right? And so another definition is that f and g defined on D residing in the complex numbers and Z0 is on the closure of D, okay, then f of z is equal to big O of gz as z goes to z0, okay, from D if there exists a delta greater than 0 such that f of z is equal to, again, big O of g of z, for z being in D, with the distance between z and z0, okay, being bounded by delta, okay? So it's just sort of a statement about the order of this function essentially as your argument approaches some limit, right? Defining that order as you approach some limit, okay, means that I can take z arbitrarily close to some limit, okay, and I get that order scaling, okay. Now note there's a special case of this, right, where let's say if z0 is infinity, right, and then f is big O of g, okay, as z goes to infinity from D, okay, if there exists an m greater than 0 such that f of z is equal to O of g z, z being in D, okay, for the magnitude of z being greater than m, okay. So so this is just a slightly different way of putting it if we're taking a limit out to z is infinity, okay. Now we can modify this slightly. In particular, if there exists some u greater than 0, such that g of z is not equal to 0, okay, when, again, z is within this bound of z0 and also in our domain D, okay, then f of z is equal to big O of g of z as z goes to z0, okay, z in D, if the limit as z goes to z0, keeping z in D as we do that, okay, I have that the magnitude of f and the magnitude of g, the ratio of those, is less than infinity, okay? So you can see that essentially this is just a related way of putting what we said before, right? You could sort of think of moving g over to the other side, okay? And then just having a constant out front. It's just saying the thing out front is constant. But oftentimes taking this limit, okay, can be more convenient than trying to prove writing it down the other way, okay?
Do we also need that limit to be non-zero, or is that not necessary?
No, because it will still be big O in that case, right?
Okay.
Big O is sort of an upper bound.
Yeah, there's not like the strictest big O in that case.
Yeah,
Okay.
right. So let's take an example, okay? Sine of epsilon is order epsilon, right? As epsilon goes to 0. How could we show that? Well, if we take the limit as epsilon goes to 0, okay, the absolute value of sine of epsilon, absolute value of epsilon, then we have the limit as epsilon goes to 0 of just a Taylor expansion, so on and so on. And this is equal to the limit as epsilon goes to 0 of 1 minus epsilon squared over 3 factorial, so on. This is equal to 1, which is bounded from above by infinity, okay? Now, you won't always have a nice Taylor expansion, right? But so sometimes you're going to have to, build up an asymptotic expansion in a different way, okay? Another example, hyperbolic cosine is order 1 as epsilon goes to 0, okay? So you can show that again by taking an expansion around epsilon equals 0, okay? Sine of epsilon is equal to order 1, okay, as, or sorry, big O of 1, as x goes to positive infinity, okay? So, to show that, you could take the limit, sorry, not x, there I go. It's sort of weird to write epsilon as going to infinity, okay? So in this case, if we write this, right, this limit is not defined, right? But we can bound it essentially, okay? So this would be bounded from above by the limit as epsilon goes to infinity of just 1 over 1, which is going to equal 1, which is bounded from above by infinity, okay? Couple more. 1 minus cosine of 2 epsilon, okay? This is going to be equal to big O of epsilon squared, okay? As,
Zach,
yeah.
So for that last example with sine, is our d then like the real axis or something?
Right. Yeah.
Okay.
So it's, you could just take the positive real axis or something like that. So yeah, it would be like 0 to infinity or something like that, excluding infinity. So then your z0 in that case would be infinity, and you would say, you know, above this value, I can bound sine between these two values. And let's just take, you know, the upper bound to be 1 then, and so you have that boundedness condition. Yeah. Okay, so for this problem, right, we have 1 minus 1 minus 2 epsilon squared over 2 plus so on and so on, right, which is going to be 2 epsilon squared plus other stuff, okay, as epsilon goes to 0, okay, from above. And the point is that in this case, you have higher order terms, right, which are going to be higher order than epsilon squared, okay? And also the constant factor is irrelevant, right? So when you write your big O notation, right, you don't need this 2 here, right? The only thing that you need is your the terms that are involved in sort of functions um, of your variable or your parameter that you're pushing to some limit in this case. Okay, so prefactors, they don't need to enter um, into your big O notation in this case. All right. Questions so far? All right. Okay. Let me do one more example, which is a bit more steps, and we'll come back to this, right? So maybe to Jake's question from before, right? We know that we can't really come up with a reasonable Taylor expansion for log of z as z goes to infinity in terms of sort of power series, right? But we can still say that log of z is going to be big O of z to the p, okay? Z is in R in this case, and this is true basically for any p greater than 0, okay? So, so this is not somehow like a tight bound on the scaling of log, but rather just, you know, some upper bound on how it scales in this limit, okay? So if we let z be greater than 1, okay, then we can write the magnitude of log of z is just going to equal log of z. I can write this as an integral, the integral from 1 up to z dt over t. This is bounded from above by the integral from 1 up to z of t to the p over t dt. So this is bounded from above by the integral from 0 up to z of t to the p minus 1 dt. Okay. So if I take that integral, then I have that log of z is going to be bounded from above by 1 over p, z to the p, okay? And I have my result, right? For z is greater than 1 in this case. All right. So that means that, you know, as log as you take the argument of log up to infinity, right? This is something you already knew, right? There's the scaling that you get for the logarithmic function is going to be slower in the large z limit than any power function with positive power that you could write down, right? So, so you would say it's big O of z to the p in this case. All right. So moving on to another definition, and then we'll talk about a few properties of order relations shortly. Okay. So let me get one more definition in first. Okay. If f and g are complex valued functions on D, some domain, that's a subset of complex plane, okay, and then Z0 is in the closure of D, so it could be on the limit or it could be on the interior, could be on the boundary, it could be on the interior. Then f of z equals little o of g of z as z goes to z0 from b, okay, and we call this little o notation. If for any epsilon greater than 0, there exists a delta of epsilon greater than 0 such that f of z is bounded from above by epsilon g of z when z is in D, okay, and the difference between z and z0 is given by this delta of epsilon, okay. So colloquially, we might say little o notation just implies that f is smaller than g in the limit, okay. So like before, we can slightly modify this, okay. And we can also say if g of z is not equal to 0, okay, sufficiently close to z0, then the following is true. F of z is equal to little o of g of z for z going to z0 and z being in D, okay? If, now I'll write this ratioed limit again, z go to z0, z lives in D. Sorry for the squeeze here, okay? F of z, g of z, magnitude, okay, of those is equal to 0, okay? So it just means that as I take the limit, okay, of this argument as z goes to 0, if I put the magnitude of f of z, okay, over the magnitude of g of z will dominate, okay, and push this ratio down to 0 in that limit, okay. So that's my little o notation, okay. So something like I know that this function will not reach this magnitude or something like that. It's can be useful for truncation if I want to sort of make sure I can throw out terms. Okay. So let's take an example, okay? And let's ask, when is epsilon to the n equal to little o epsilon to the n in the limit as epsilon goes to 0, okay? And the answer is basically whenever this power is greater than this power, right? Because I can always take that ratio, take that limit, and that ratio will go to 0. Okay. So essentially this happens whenever n is greater than m. So when the limit as epsilon goes to 0, epsilon to the n over epsilon to the m is equal to the limit as epsilon goes to 0, epsilon n minus m is equal to 0. Yeah. So I can say that epsilon to the n equals little o of epsilon to the m as long as n is bigger than m. Okay. That maybe gives an example where you have some intuition for how little o works as opposed to big O. Okay. One more example. Okay. When is exp of minus 1 over epsilon equal to little o of epsilon to the p? Okay. Remember the notion of being exponentially small. Okay. And let's take, in this case, just the right-hand limit. So as epsilon goes to 0 from above. When is this true? For what values of p? Another way of saying is, think about how you could, attempting to Taylor expand that function around epsilon equals 0. Are you going to get any terms in that case? Okay. You're going to have uncomfortable sounds. So this is true for any p. Okay. This exponentially small limit, okay, is going to be smaller than any algebraic powered function, okay, you could take. So in the limit as epsilon goes to 0, right, this is going to vanish always much faster than this function will, okay, no matter how high I take the power of p in this case, okay. And again, I mean, you could just go through this calculation to check when this is true, okay. And the limit as epsilon goes to 0, e to the 1 over epsilon, absolute value of e to the p. If we use, L'Hopital's rule, we can use L'Hopital's rule essentially as many times as we like on this, right? And we will eventually eliminate the term on the bottom, okay? And we will still retain the term on the top, okay? So this will go to 0, okay? Well, the term on the bottom will stay constant. So this is going to be equal to 0, basically for any p, okay? And you can try showing on your own, let's say with L'Hopital, okay? So that's little o notation, okay? Before we move on, let's catalog a few properties of order relations, okay, both of little o and big O, okay? First of all, okay, if f is little o of g, it actually implies that f is also big O of g, right? because remember, big O is not a tight bound, okay? And little o is a more restrictive bound than big O, okay? If f of z is big O of 1 for z living in B, this implies that f is uniformly bounded in D, right? There's nowhere in D that f is going to diverge. I can always bound it from above by some finite constant, okay? If f is little o of 1, okay, as z goes to z0, this implies that the limit as z goes to z0 of f of z is equal to 0, right? Because I would just write this with f of z over 1, right, in this case, and I would get the limit 0 in that case. Another property, if f is big O of g, and we have some a greater than 0, then the power of f in A is equal to big O of magnitude of g to the 8th power, okay? And this holds for little o too, okay? So I can always, pass through some power function of A. This can be helpful, like, if you have some function that's, shrouded in a power that you need to sort of undo, okay? Summation. If I have a bunch of functions, and I call them fi, and they're each big O of gi, where I is some index that goes from 1 up to n, okay? Define also some coefficients from I equals 1 up to n that live in the complex plane. Then what I can do is take a linear combination of my functions, and that will be big O of the linear combination of the magnitudes of my coefficients times the magnitude of my functions gi there, okay? So, it's not quite like big O is like a, linear operator or something like that. And in fact, you get these nonlinear relations too, but you can perform linear summation and you get something like linear summation of your big O function, okay? Another property, okay? Big O of g, if f is big O of g, and if g is big O of h, okay, then we get some transitivity where you can say that f is big O of h, okay? And that's not too hard to prove, but I'll just write it for now, okay? Another property, if we let x be in A to B, and we say that f is big O of g as x goes to B, okay? And we say that f and g are integrable, then the integral from x up to b of f of t dt is equal to big O of the integral of x up to b the magnitude of g of t, this integral from x up to b, okay? As x goes to b on a, b, okay? All right, that's all the properties I'll list for now. These will come in handy as you're trying to characterize the order of functions that you might come across and their asymptotic limits, okay? One more definition sort of related to these properties is that of uniformity, okay? So now I'm going to write, let's say f is some function of x and it's parameterized by epsilon, okay? And I can similarly, okay, write g as a function of x and parameterized by epsilon, and that's a big O bound on f, okay, as epsilon goes to 0, okay. So you have uniformity, okay, of this relation if it holds independent of x in some domain B. Okay. So I have a uniform big O bound, okay, as long as it holds for any x in my particular domain. All right. So just to take an example, sine of x plus epsilon equals big O of 1 uniformly for any x that lives in R as epsilon goes to 0, okay? So no matter what value of x I take, right, sine is just going to oscillate between -1 and 1, okay? I always know that the limit as epsilon goes to 0 for this is going to give me some function that I can bound by a constant, okay? Another example of uniformity is if we take e to the minus epsilon t minus 1, okay? This is going to be big O of epsilon because I'm subtracting off the one part of the Taylor expansion there, okay? But, okay, it's going to be non-uniformly, okay? And why is this going to be non-uniform on the, let's say the half line from 0 to infinity, okay? Well, in order to demonstrate this, if I take t to be equal to 1 over epsilon, okay, and then I evaluate my limits, okay, I'm sort of canceling out uh, my ability to sort of shrink things down to order epsilon, right? So if I'm allowed to take t to be any value from 0 to infinity, I can always sort of just keep pushing t out to higher and higher values, and it's going to counteract the limit that I'm taking here in this case, okay, because t is allowed to take on basically any finite number I like, okay? So in this case, e to the minus epsilon t minus 1 equals big O of epsilon, okay? This is going to be uniform, okay, on t in some bounded region 0 to a, okay? Basically for any 0 to a to infinity. Okay. So as long as I restrict the upper bounds, okay, to be something that's not, just an open interval going all the way out to infinity, then I can always say, well, I could push t all the way up to the, just below the boundary of this region, right? Up to just below a. And I know that then I can take my limit, epsilon goes to 0, and I will shrink down terms in my Taylor series and get something that's big O of epsilon in that case. Okay. So that's something to consider when you're writing them. Big O notation for a particular bounded region. Okay. So that's properties of order relations. We've introduced sort of big O and little o notation. We talked some about uniformity. Next time, we'll introduce uniqueness of asymptotic expansions. We'll talk a little more about what makes a particular asymptotic expansion. And then we'll, maybe not on Friday, but probably on Monday, we'll start getting into asymptotic approximations of integrals. Any questions before we conclude for today? All right. So yeah, if anything comes up on the homework, you can, sometimes I can answer stuff by email if it's brief. If it's sort of a lengthy question, though, we can try and schedule a quick chat over Zoom. I'll make it if I can. Otherwise, yeah, make sure you wrap up that homework and upload it to Canvas before class on Friday. Okay. All right. We'll see you all on Friday.
Thanks, Zach.
Yep. Thank you.